Ngalakin Khadijan Nyunga Boja.
Okay, hello. Welcome to today's module for Signals and Systems, where we will continue the story of the response to a continuous time system. We have discussed the zero input response and introduced the convolution integral. So today we'll look at the zero state response. So let's see how we get that and the relationship between the zero state response and the convolution integral. So let's start by sharing my screen. And here we go to the lecture notes. Now, how do we work out the zero state response? Remember, what is the zero state response? It is the response of a system to an input where there are zero initial conditions. So the initial conditions are all set to zero. The only thing the system will do is respond to the input X. So what we want is to work out the output Y of the system T to the input X. And we're deliberately using the notation of T that we learned about in chapter 1 because it's going to be very convenient to see how we do this. First of all, we need to define something called the impulse response of the system. And this is a linear time invariant system. If you excite the system by impulse function, then we say that the output of that system to the impulse function is something called the impulse response. Makes sense, it's the response to an impulse function. And we have a special label for that impulse response, which is h of t. So whenever you say h of t, you may be referring to the impulse response of the linear time invariant system. And that response is very important. There's a lot we can work out from that response. So what is the impulse response? Okay, the impulse response represents the system being energized by an impulse. So it allows one to capture the general behavior of the system. In practice, it's a short burst of energy applied at the time that we want to look at the response of the system. So typically it's applied at t equals 0. And that energizes the system and allows you to capture how the system will behave to at least a very short, sharp input. However, the way it's defined mathematically in chapter 1, this guy here, is you can't really realize it because it's not defined for t equals 0. The point where you're applying it is t equals 0. So in practice, you really have to think about what it really means for a real physical system. And what you simply do is model it as a pulse that is applied to the system for a very short duration and a lot of energy. In other words, it's got a very long height. The height is high, so the amplitude is high. In mechanical systems, which ironically are perhaps easier to understand, and some of you may have actually come across this if you have an experience with musical instruments or other mechanical devices, is to get something called an impulse hammer, and you literally hammer or hit the device, and that hammer acts as the impulse. That hitting generates a sharp burst of energy, and how the response resonates, decays, or transfers the energy is your impulse response. And with the impulse response, you can work out the response of the system to any input. How do we do that? Well, now we're going to make use of everything we've learned in chapter 1 and also chapter 2. For example, do you remember the shifting property of the unit impulse function? If not, revise chapter 1. Now you notice I'm staring across. I have to get used to staring in front of the camera. So if my eyes wander, it's because I'm looking at my photo on the side of my screen. In fact, I'll move that across here. I'm not sure if that happens when it's recorded. So we have an input, and if you remember from the shifting property, this is what you see. So the convolution of the input with the unit impulse is equal to the input itself. So you notice the first use of the convolution integral. What it really means is that you consider the input as an integral, or more correctly, as a summation of little impulses that go across the input. You notice x tau is actually values of the input at all the values of tau that it exists from negative infinity to plus infinity, and at each point you just have an impulse. And if you sum it across all the values, you will get the actual definition of the input. So what happens now is, let's say this input is applied to our system. That's what we have. Replace that by its integral, convolutional integral form, which is what we have here. Now, how does this system behave to this quantity that's been applied to it? This system responds to an input which is a function of time. So the only quantity here which is a function of time is the impulse function, because it's a function of time here. This x tau is really an artifact of the integral. The only thing which is really operating as a function of time is the impulse function. So we apply t through the integral like that, past the x of tau. X of tau is effectively behaving like a constant as far as the system is concerned, because it does not depend on time. It just depends on the integral form. And the only thing we're left with is the impulse function being input to the system. Of course, it's the impulse function delayed by tau, as far as the system is concerned. Now, remember two things. The system is time invariant. And we also remember that we've defined the impulse response as this. So since it's time invariant, if you delay the impulse, you delay the impulse response. And that, of course, is the same as that. So guess what? That gets replaced by this. And you're left with the most important result you ever find, which is that the zero state response is given by the convolution integral, yes, of the input with the impulse response. If you can evaluate that integral, then you'll get the output, the zero state output. This also allows us, this view here, to view the convolution integral in an alternative format, which allows us to understand exactly what we have done. So this is a different view. And what I mean by a different view to what we had here. If you remember, this is the graphical explanation of the convolution operation. And most textbooks and most demos will actually show you this. But for us, what's important, now that we're looking at the zero state response, is what exactly that means. So let's go back and depict what we've just done. So what we've just done is said this, that the output is equal to the convolution of x with the impulse response. And we've also said that the input is a convolution of x with the unit impulse function. This one, or this fact here, and that fact there can be connected graphically over the page as shown as follows. So this is what we're going to do. Now the caption explains what we're trying to do. So let's try to describe what we're seeing here. We consider a pulse function, very short duration pulse function, height of 1. And this delta will get smaller and smaller. We can consider our input as a linear sum of these different pulse functions, which are applied at different points in time and have different scales. In fact, it's actually a linear combination in terms of time shifts, in terms of amplitudes. So this is the amplitude, which follows that, and the time shifts are the positions. And we take, for example, a particular time shift, which we say is n delta tau. So we have the first one is here, then the second one is next to it, the third one, and so forth. So we stack these pulses across from here to here to here, until we get to there. In fact, here probably it's better to expand this to see that. So that's the one pulse, the next pulse, next pulse. It's a linear combination. Now let's abstract this as a unit impulse function, like that. It generates an impulse response, by definition, h of t. Let's delay that unit impulse function by n delta tau. So it's delayed here. It's a time invariant system. So the same impulse response is delayed by the same amount. Let's now multiply this, scale this by the value of x at that point. So this has been scaled up, and this also gets scaled. So now what we do is we say, okay, if x is synthesized as a linear combination of these impulses, and since the output to one of these impulses gives us the impulse response, then when we apply this impulse to the system, since it's linear time invariant, in fact, what we can say is that the output of the system is the same linear combination of the responses of these pulses here. So each of these is a unit impulse. It will generate an impulse response at different spacings, and the sum of all of these is yt. And that's what we see here. So each of these is in fact a impulse response function to one of these pulses at a particular n value or position. And the height of these follows the input. So for example, just to show you how this would look, if I draw a straight line, here we go, like that. I'm not very good at drawing straight lines. Now, I'm not sure, let's see what happens here. This should be interesting. If I expand this, so I thought, okay, it sort of works. What I want to show is that if you want to work out the output of y at this point in time t, you've got to sum all those lines that you see there, the solid line and all these dashed lines. These are the response of the system to the input at all previous times. So at this time, when the first input arrives, its response goes like that and appears here. A later one appears there. So that's why I have an integral expression. It's actually summing all the responses up to the point t, time t. So this is all added together to give you the total response. That's, in a way, another way to view the convolution integral. And it's a sort of a variation of the graphical explanation. If you're finding this a bit hard to visualize or see, maybe the mathematics may make it easier. So let's look at the mathematics behind this and what we've done as well. Let's get rid of this as well. So what we've said is that the input is equal to the sum of these pulses spaced at different times and the height. We've summed them for all n, and because to make the approximation approach x, we have to take the width and make it shorter and shorter. We have a larger and larger number of impulses spaced closer and closer together. And we take the limit as that tends to 0. That, in fact, ends up being this convolution, which is the sifting property. Because as delta goes to 0, a summation becomes an integral. Now, our y is equal to what we saw here, the sum of these for all the values of n. That's what you have there. And that's what you have here. Once again, delta goes to 0, so this summation becomes an integral. That's what you get, and that's exactly the result we want to show. So now you know how we work out zero-state response given the impulse response. What we need to do, of course, something that I've conveniently not mentioned, is how do we derive the impulse response? I'll come to that shortly, but let's do a quick calculation just to get a feel for using the convolution integral in this context. So let us look at an example where the impulse response is given as this. Good news, this is not unusual. In fact, this is an expected impulse response. As we will see, the impulse response follows the characteristic behavior of the system, so it will look like a zero input response. In a sense, it's got the same form. And if you remember earlier on, the module looking at the zero input response, what we showed was that the exponential is exactly what you see. be it for real distinct roots, repeat roots, or complex roots. So this is pretty much spot on what the impulse response will look like. In terms of the input, we're going to make the mathematics easy for this problem, and we assume the input is also an exponential decay. That is not so common. Inputs are a bit more versatile. The most common input you'll see is a sinusoidal input or a step. Usually those are the most common type of inputs we like to apply and test the system with. Of course, the input could be any arbitrary signal that you can imagine. But for this case, we'll just assume it's a straight decay. So this is a convolution integral. Now, x is replaced by this, and that's what we see here. So the t becomes a tau. This gets replaced by that, so this becomes t minus tau. Now you notice something funny has happened here, and it's easy to miss when you go and review this. First of all, what's happened to the unit step? It's there, it's not here. And you may think this perhaps is related, and it is. Why have we changed negative infinity plus infinity 0 to t? It is the unit step effect. How does that work out? Well, I'll tell you this. I've seen students go ahead and replace x and h by x with a unit step and h with a unit step. So they would have u t minus tau with the negative infinity and plus infinity. I think mathematically that is correct, and you can probably solve for it. But to be honest, I would get stuck because I really don't know how you would proceed when you effectively have not 1, 2, you have 4 functions there, x, u, h, u. And the unit step, how do you handle that? Here's how you handle the unit step. And in this context, this is the only way you should really handle it. If you look at this and you understand what this is telling you, it's telling you that x only exists for positive values of t. The unit step is acting as a switch. And if you think of it as a switch, it makes your life a whole lot easier. So that means x of t is equal to e exponential minus t for positive t. So we only consider this integral for positive values of t greater than 0, because if x is equal to 0, the whole integral is equal to 0. So in this case, we don't need the unit step once we make the lower limit 0. Same applies to this. This also only exists for positive values of t. In this case, it's t minus tau. So t minus tau has to be greater than 0, which means tau, the variable of integration, is less than t. The upper limit is t. Remember that. Some students don't realize this until they actually start doing some questions and then wonder what's going wrong. And then they go back to this and realize, wait a minute, what exactly is going on here? That's why you should never take things on face value. Be sure you understand 100% when you go from this step to that step. So the rest should be straightforward enough. This is an integral with a variable as tau, so the e to the minus 2t can be taken outside the integral. You're left with that. That's an easy integration, and when you multiply through the e to the minus 2t, the final answer is this. That is your zero-state response. And the fact that it only exists for t greater than 0, we put in the unit step. Once again, the unit step acts as a switch to tell you it only exists for positive time. If you want to, you can try to work this out using the graphical method. I won't go through it here. It's the same approach. It's the same approach we showed previously with in the previous module. And what you see here, you should really be plotting this function here. For this form here, where you have easy, continuous functions, you probably find that this will be easier to calculate directly in the integral rather than trying to do it graphically. In fact, doing it graphically is always going to be difficult no matter what. And as I said, in the other module, when we do the tutorials, you'll actually see how we try to consolidate the two with waveforms which are piecewise, like convolving a rectangular pulse with a triangular shaped waveform. The integration of that, the convolution of that is not as easy as what we do here. Now, the question still remains to be asked. How do you obtain the impulse response? Well, you can use the hammer effect if it's a mechanical system, which means you apply a short duration of high energy. But sometimes that is difficult. If the energy is too high, you may destroy the system in the process of testing it. So you have to be careful. Another cool way of doing it is to apply a unit step. In other words, the input is a unit step. You will get a response, and you can show, and we'll show later on when we look at the Laplace transform in the latter part of the chapter of this that we're looking at here, chapter 2, that you can then differentiate the step response to obtain the impulse response. So that is usually a more convenient way to do that. Now, there is a formal way that you can find, and it's in one of the textbooks, where you can derive the impulse response in the same way we derive the zero input response, by looking at the characteristic equation and working out how to derive from that. That technique is not that commonly used because we end up going to the Laplace transform, which comes up with a more elegant and straightforward approach to directly get the impulse response. And in some cases, for what we do as engineers, we don't even need to work out the impulse response. In other words, we don't directly have to work out the impulse response depending on what we want to do. So having to work it out directly is not as important, for our cases, because we would use the Laplace transform. Since we have not yet looked at the Laplace transform, here we have to work out what the impulse response is. So with such questions, you'll be given the impulse response. But what is the impulse response? Well, guess what? It is of the same form as the zero input response. That probably makes sense, because if you hit something with an impulse, you're effectively just energizing it, and then the system will respond in the same way it would respond if it had some state energy. So even though you say it's zero state, when you hit it with an input, you actually create initial conditions, say, on your capacitor or inductor. And the system will probably behave in the same way as it would with a zero input condition, where you just look at the states. So it is not surprising at all that the impulse response and the zero input response look very, very similar. Okay, let's consider example 2.3 that we looked at in the module on the zero input response. This was the circuit. That was the input. Now we're going to try to work out what the zero state responses, or always, as you say here, the zero state component of the total response. Now, the zero input response we had from example 2.3 is that. In case you forgot, let's go to example 2.3 and I'll show you. Okay, I just paused the recording and started, so that's why it's jumped. So if you remember, this is example 2.3 when we looked at the zero input response, and we found finally, after a bit of calculation, that this was the zero input response. So now we want to look at the zero input response and compare it to the impulse response. So this is the zero input response that we just saw. Let's reorder it, because we need to now compare it with the impulse response, which, if you look at the textbook, one of the recommended reading textbooks, it's worked out to be that. Compare the impulse response with the zero state, and you will see that e to the minus t, e to the minus t, e to the minus 2t, e to the minus 2t. So the exponential forms are exactly the same. What has changed are the coefficients. That's 5, that's 2, that's -5, that's -1. That would imply that the initial conditions that you use for the impulse response are different than the initial conditions that you use for the zero input response. That makes sense, because the zero input response is due to the state before the system, from some arbitrary function of the system, and the state is pretty much given to you, whereas the impulse response is a very well-defined system, the system you get when you hit it with an impulse. So you're bound to generate different initial conditions, and that's exactly what you have, a different coefficient, but the response format is exactly the same. To get the zero state response, then it's just a small step to take that, plug it in here. That's your impulse response. That's your input, which, if you recall, was this. That was the input. As we've done before, this goes from 0 to t. That's the input. That is the impulse response. This time I'll leave you to work out the calculus, the integration. These exponentials are quite easy, slightly more tedious than the previous one, and this is what you get. And you notice 3 terms. This term and that term are to do with the impulse response, or more correctly, the zero input characteristic modes. This one here, the e to the minus 3t, is to do with the input. And that's pretty much what we tried to show right at the beginning. Remember? Total response is equal to zero input response plus zero state response. And you see that here. And what we'll do now, just to finish off, is do exactly that. Work out the total response and then show some of the connections between the zero input and the zero state. So, after all is said and done, the total response now is just, for this problem, that. It's equal to the zero input response plus the zero state response. Remember, the zero input response comes from the characteristic modes, which are the lambda k, and you work out the ck from the initial conditions, the state of the system with no input, and the zero state response is the response to the input, where the state is 0. So, given that we've already worked out the zero input response from example 2.3, and we have just now worked out the zero state response, we add the 2 together, and we finally get the total response to the input and to the initial state. And this is what the system will respond. That would be it, but we need to mention, special mention of different terminology. And in some textbooks, depending what the discussion is, maybe outside engineering, there is mention of something called a natural response and forced response. What do these two terms mean? Well, the natural response, where we use the subscript n for natural, includes only and all the terms that are related to the characteristic modes of the system. Whereas the forced response, with the subscript f, only includes the terms which are strictly related to the input. So if you look at this here, I can tell you that are the terms to do with the characteristic modes, which of course from the zero input, e to the 2t, e to the minus t. So this would be the natural response of the system. What you see here, strictly related to the input, which was 10 to the e minus 3t, if I recall, is the forced response. Now, let me see if I'm correct. Did I get it right? I think so. That's it. Forced response, natural response. And you have a third category. Guess what? The natural response usually decays with time. Certainly that's the case here. Because with energy, the natural response would be to dissipate the energy and slowly decay, either in a damped manner like that, or when you have complex characteristic modes in an oscillatory manner, it slowly decays. And this, because it decays, can sometimes be referred to as a transient response. You're now, gone soon. It won't last for long. The forced response lasts as long as you apply input. And when we consider inputs like a unit step, which goes on forever, or a sinusoidal, which goes on forever, the input can last forever. So we call it a steady state response. Effectively, the steady state response is what remains after a long time, because the transient response would have died away. The example here is not very good because the input is also an exponent. It's an unfortunate input that we apply to the circuit. Let me go back to the original question. This was for mathematical convenience, but this input will die away with time. So in a sense, the transient response dies away, and the steady state response is really transient because this also dies away. The question is, in practical circuits, what would you normally have here? You probably have a unit step, a constant voltage, and that certainly does not die away. Or this could be AC, alternating current, alternating voltage, so it would oscillate. Both AC and DC voltages would not die away with time. So they would be what we call the steady state response. Unfortunately, we did not do that here, as I said, for convenience. And that is it. We'll leave the next section, system property and stability, for another module. Thank you for listening, and see you again next time.